A subsequence is a sequence that can be derived from another sequence by deleting some or no elements without changing the order of the remaining elements. Suppose we are having a sequence of natural numbers. Let's take that. 1, 2, 3, 4, 5, 6, so on. This is a sequence of natural number. And now I'm getting my subsequence as, let's remove all the even numbers from this sequence, right? So what I got? 1, 3, 5, 7, so on. So this is a subsequence for this sequence of natural numbers. Even you can remove the odd ones and you will getting the subsequence for the even numbers, right? So I have not disturbed the order of other elements here. I just delete or remove some of the even numbers from this sequence. So I get this subsequence as a subsequence from this sequence. Now is the definition for subsequence. Let nk be a strictly increasing sequence. What does this k represent? This k is your subscript, right? With nk belonging to natural number. That is, if you're having n1, n2, n3, n4, these are the elements of the sequence. And it is an increasing one. Increasing one means your n1 is smaller than n2 and then n3. It is increasing. And these all belonging to your natural numbers. Then this 1, 2, 3, these represent the subscripts. Then the sequence Pnk is called subsequence of Pn. For example, suppose I am having my sequence Pn to be equal to P1, P2, P3, P4, P5, P6, so on, right? What I have done, I deleted the P1, P3, P5 from the sequence. And I get my new sequence as Pnk, that is a subsequence, having the elements P2, P4, P6, P8. Now the subscripts are 2, 4, 6, 8 here. And in the Pn sequence, subscripts are 1, 2, 3, 4, 5, 6. So can I write the subscripts for the subsequence as P2n? It is twice the natural number, right? If this is my Pn, then my subsequence will be P2n. And Pnk is nothing but this nk also representing the subscripts, right? So this is a subsequence for Pn. Okay, right. Next, one more definition is there for subsequential limit. Let Pnk be a subsequence of Pn. If Pnk converges to P, then P is called the subsequential limit of Pn. Whenever your subsequence converging to a point, then that point will be the subsequential limit of main sequence. That is Pn. Okay, let's do a theorem for this subsequence. If Pn is a sequence in a compact metric space X, then some subsequence of Pn converges to a point of X. Now we have given a compact metric space as your X, and we are having a sequence Pn in this metric space X. Then there is some subsequence of Pn converging to a point of X. There is a point in X to which the subsequence of this Pn sequence converges. Right? This we have to prove. Alright, let's start with the proof. Suppose we are having a Pn sequence in a compact metric space X. Okay, you know what is the range of the sequence. Suppose my Pn sequence is, let's say -1, 1, -1, 1, -1, 1, -1, 1, so on. What is the range for this sequence then? Range is the distinct elements. So what are the distinct elements in this sequence? -1 and 1. So this will be a range for this sequence Pn, right? So what I will do, I will consider the range for the sequence Pn to prove this result. Okay, and I'm considering that range to be as E, which is also, now if the sequence is contained in your compact metric space X, then this range will also be contained in that compact metric space X. Fine? Okay. Now what you will guess in this Pn sequence, you can have a subsequence. See, this Pn sequence can be converging to -1 or 1, right? So what will be the subsequence? Can I manage the numbers as I will collect? This is suppose your P1, this is P2, this is P3, this is P4, P5, so on. I'm collecting this positive numbers, that is P2, then P4, then P6. This will be my subsequence for positive number 1. 1, 1, 1. I can also have my subsequence to be as of negative number, that is P1, P3, P5, so on, -1, -1, -1, -1. What is actually happening? This subsequence is converging to 1. This subsequence is converging to -1. This we all need to prove. That if we are having a sequence Pn, then some subsequence of Pn converges to a point of X. So I have found a subsequence for this sequence Pn as P2, P4, P6 or P1, P3, P5, which are converging to a point 1 or -1, right? So what we are saying that this P2 is equal to P4 is equal to P6, so on, and it is all the terms are equal to a point P. You can say that point to be as this, just for an example 1. Right? So whenever your range is finite, you can have a subsequence which is converging to a point which is belonging to your compact metric space X. Right? This I have to just write now. This is the proof. So two cases arises. If your range is finite, then we take this example. If my range is infinite, then we take the help of the limit point. Okay. So we just take a sequence and just see about its range and prove the result. So I'm writing this now. Let E, consider this E to be the range of the sequence Pn. Alright, then this range E is also the subset of compact metric space X, right? Now the case 1, because range can be, we don't know about the sequence, range can be finite or it can be infinite. Suppose the case 1, the range is finite. If E is finite. Then what will happen? Then there exists a point P belonging to this range E and a strictly increasing sequence Nk, where your Nk belongs to the natural number, such that this Nk is a subscript for the subsequence, right? You remember Pnk, right? This Nk, for a sequence you write the subscript n only. For the subsequence, we write the subscript nk. Is it clear? Right? So we are getting this subscript for the subsequence such that we know that Pn1 is equal to Pn2 is equal to Pn3, so on, which all the terms are equal to the point P. Why this will happen? I have explained to you that I have taken the sequence, okay, I'm writing over here, I have taken the sequence -1 the power n, right? And the sequence for n equal to 1, this is -1, n equal to 2, this is 1, for n equal to 3, this is again -1, n equal to 4, this is 1, -1, 1, so on. Just take the example of this sequence and manage this proof. Now some of the terms of the sequences are same, and that is equal to P. P can be 1, P can be -1. You can take either of the point. Okay. So thus, if the points are equals, if most of the points are equal to the same point P, then we got a subsequence which is converging to the point P. Evidently, we got the result. Thus, the subsequence P and K. Remember, we write Pn for the sequence, we write P and K for the subsequence. P and K, this is P. If K is equal to 1, this is Pn1. If K is equal to 2, this is Pn2. If K is equal to 3, this is Pn3. These are the elements of the subsequences, right? Now the subsequence of Pn. This is P1. This is P2, this is P3. So obtained evidently converges to P, which is contained in, which is the element of the range E, and further this range is the subset of X. That is, P is belonging to X. So the sequence converges to a point of X. Hence the sequence converging to a point which belongs to X only. Right? So this is just your example for checking the proof. Now the other case, if your range is infinite. Case 2. If E is infinite. Alright, now if E is infinite, then we will guess a limit point. So then E has a limit point P in X. This is a theorem, that is, if you're having a subset in X and if that subset is infinite, then that subset has a limit point in X. So if E is infinite, let's say, then E has a limit point in X. Now remember the definition for the limit point. Now because E is infinite subset of a compact set X, whenever you're having a limit point P for the infinite subset, then every neighborhood of P contains infinitely many points of E, right? Whenever you're having an infinite set, and if you're having a limit point for that set, then every neighborhood of that limit point contains infinitely many points of E, right? Now let epsilon positive be given since, say, P be the limit point of X. Then E has a limit point P in X. Since P is a limit point of E, right? Therefore, every neighborhood of P contains infinitely many points of E. Say Pn1, Pn2, Pn3, so on. There are infinitely many points. Say Pn1, Pn2, Pn3, so on, right? Where this n1, n2, n3, this must be a strictly increasing sequence, right? So where nk is the subscript of the terms of the subsequences. This is a strictly increasing sequence. Why I am writing strictly increasing sequence? Why I am forcing on this word strictly increasing sequence? Because the order of the elements should not be disturbed. Suppose you are having the sequence of natural numbers, right? And I am getting the subsequence from this as this 2, then 4, then 6, right? This is your Pn1. This is your Pn2, this is your Pn3. So if this is P1, this is P2, this is P3 for your sequence, and this is P and K as your subsequence, what is this 1, 2, 3? This is increasing in, this is increasing, and this n must belong to the natural numbers. And 1, 2, 3, the subscripts, see the subscripts, 1, 2, 3, these are increasing in number. And now the terms for the subsequences. Pn1 I take 2, Pn2 I take 4. So this must also be increasing. If I do not write the word increasing over here, they can take as first one Pn1, then Pn3, then Pn2. The sequence will be disturbed then. They can think of Pn1, then Pn3, then Pn2. So sequence is disturbed. So I must write strictly increasing sequence so that the order is managed. So that the order of the sequences is maintained. Here also strictly increasing sequence, and here also subscripts should be strictly increasing sequence. They should be in strictly increasing sequence, right? So this is very important to write over here for the subscript to be as a strictly increasing ones. All right. Now thus I got my P and K as a subsequence of Pn in E. In E I got my subsequence for Pn such that what is happening, all these elements P and K, these are belonging to, because P is the limit point of E, and limit point of P, the neighborhood of the limit point of E, is containing infinitely many elements of E. And I took those infinitely elements to be as Pn1, Pn2, Pn3. That means all these elements are contained in the neighborhood of P. That is the neighborhood of the limit point. So can I write P and K belongs to the neighborhood of P? Yes. Yes. What does this mean then? the points are in the neighborhood of P having the radius epsilon. That means their distances from P is less than epsilon. Suppose you are having the neighborhood as P and the radius is epsilon, and all the points, infinitely many points, are lying in this neighborhood of P. We say that these points to be as P and 1, P and 2. That means your P and K is belonging to this neighborhood, and the distances of all these points from this point P is less than epsilon because these are contained in the neighborhood of P. So can I write after this as distance for these points with this P is less than epsilon for this K greater than equal to 1. Fine, because the number starts from 1, P and 1. So this K should be equal to 1 or greater than 1, right? But epsilon was arbitrary. Do you remember the definition for the convergence? Whenever the distance of the points with the single point less than epsilon, then we say that this element, all this sequence is converging to the point P. This is the definition for the convergence. So what does this imply? That P and K is converging to P because their distances with P is less than epsilon. This is the main definition for the convergence. In the very first video you can check. So this P and K is converging to P. From this I have written P and K is converging to P. So my subsequence, what is P and K? The element for the subsequence. So my subsequence is converging to P, right? So at the last I'm writing, thus P and K is a subsequence of Pn which converges to P which belongs to X. Hence the result. So two cases you need to prove for, that is if the range is finite, then if the range is infinite. So thank you for watching this video. I hope you understand. So next time we will be doing Bolzano-Weierstrass theorem and some more theorems on this subsequential limits, and then is your Cauchy sequence